So welcome to the first of these video tutorials on circular motion, and we're actually going to start this tutorial on talking about a scenario. We have a penguin that's standing below on level ground, okay, and so we know that if there's no other forces present and they're not accelerating vertically, that the force of gravity is equal to the normal force. Okay, so that is nothing new there. But consider this. That ground that the penguin is standing on is the Earth, and the Earth is rotating. So then the question becomes, what allows it to turn the corner? So recall that there's three ways to accelerate: speeding up, slowing down, or turning. So if we're turning, then what we know is that there must be a net force. And then what that means is that the F net is not equal to 0. So then we cannot have F of G equal to F of N. Okay, so how can we? Okay, and the answer is that we cannot, the forces cannot be balanced. Okay, as a matter of fact, what we know is that the force of gravity must be greater than the normal force. We'll talk a bit about that in just a moment. And if the Earth is always rotating, then the force of gravity is always equal to the normal force, and the direction is always, of the acceleration is always directed towards the center of the Earth. Meaning that at any point in time, my acceleration vector is directed towards the center of the Earth. Okay, and we'll speak a bit about that in just a moment. So what's the point of this scenario? Well, first of all, what we want to do is we want to establish that anytime an object moves in a circle or a curve, it's always accelerating. So this is nothing new. We're just formally talking about it now, accelerating. Because it's always constantly changing the direction. So it's the direction of the velocity, not necessarily the magnitude of the velocity. What I mean by that is the object could be going at the constant speed and turn, and that is by definition an acceleration. And then the direction of the motion is always off on a tangent, meaning that if for some reason the Earth stopped spinning and the duck was on it, the penguin was on it, that the penguin would go off with a velocity vector in that direction at that moment. So we say that it is tangential. And all that means is that it is tangent to the circle at every point. And the acceleration is always inward. And the fancy word that you see for inward is the centripetal, which comes from the Greek for center seeking. And if we want to calculate the magnitude of that acceleration, we know that the equation for acceleration is change in v over t. But if we don't know t and we want to relate that just to the velocity and, as a matter of fact, the radius, the centripetal acceleration is v squared over r. And it's important that this equation only applies that if an object going at a constant speed. Okay, notice constant speed, not constant velocity, for the reasons that were just addressed. And when you think about how one would calculate speed, speed is the definition of average velocity is the displacement over time, the change in position over time. So if you think about the penguin going around and spinning around the Earth, well, its change in position, its distance traveled, is the circumference. So when we talk about velocity for something going in a circle, it's the circumference divided by how long it takes to go around once. We call that the period. So, and you guys know from your math class that the circumference of a circle is calculated by 2 pi times r. So this is 2 pi r over t. So let's try a few examples here. Okay, so we have an Earth radius and we have a period, it's 1 day. we want to know what the tangential speed is at the equator. So we have v equals 2 pi r over t. This is 2 pi times the radius of 6 times 10 to the 6th divided by the period 86400. And if you go through and punch that into your calculator, you get a value of 436 meters per second. If I want to know the centripetal acceleration, well, that's the v squared over the r. So that would be 436 meters per second squared divided by the radius of 6 times 10 to the 6th. And when I did that, I got a value of 0.032 meters per second squared. Okay, so not a big acceleration, which shouldn't be that surprising. If I want to know what the normal force is on that penguin, a 20-kilogram penguin, what I want to do is I want to first draw a free body diagram. And what we said before is that the force of gravity must be greater than the normal force in order to accelerate inward. So let's draw my free body diagram to show that. There's my force of gravity. I'm going to over-exaggerate. There's my normal force. And if I sum my forces and set that equal to ma, I can write it as, since I know it's accelerating downward, I'm going to make down positive. So it's my force of gravity minus my normal force equals ma. And then I can add my normal force over, subtract my ma, double check my algebra, but the normal force should be the force of gravity minus ma. And so the force of gravity, as a matter of fact, actually I did one extra step with algebra. This is mg minus ma, which is m times g minus a. So go ahead and try plugging that in and see what you get for your normal force. Pause the video if necessary. So I got a value of 195 newtons. Okay, which once again isn't so far off of what you would have had if the Earth were not spinning. So if we want to talk about by what factor the acceleration changes if we change the rotational speed, okay, you can imagine that if you have the Earth and there's the equator, when you're at the equator, that is when because there's the axis of rotation, so that is when you're traveling the greatest amount of distance simply because you're spinning around the full circumference of the Earth. Versus if you're at, let's say, here in Canandaigua at 43 degrees north of latitude, that you're closer to the pole, so you're closer to the axis of rotation. So you're not spinning as far. So your R is changing. So we want to know how, and also your V is changing likewise, because it takes the same period, because it's 24 hours in one day to rotate around once. So we want to know is by what factor will our acceleration change. So there's two pieces of this. We want to first evaluate what would happen to my velocity. So 2 pi r over t, I'm cutting the radius in half, and so that is going to how I get half the velocity. And then I have half times my velocity, but I also, the way I had to get that was cutting my radius in half as well. So I have a half squared over a half, so that works out to be 1/2 times the acceleration. Half squared is a quarter over a half is a half. So 1/2 my acceleration. Okay, so important things. We know that the direction of the acceleration is always inward. That's what we mean by centripetal. And if we take a look at some graphs, and actually I added a third one here, this centripetal acceleration versus the period. If I want to look at A versus R, my equation is A equals V squared over R. So I could say that A is proportional to V squared. Basically just saying if R stays the same, what's the relationship between A and V? So that's going to be my squared relationship. So it's going to be a quadratic. Same equation, and if I'm looking at how A is related to R, this is staying, if I get rid of V basically and change the equals to a proportion sign, A is proportional to 1 over R, so that is an inverse graph. And then if I want to figure out what A and how A and T are related, I have to do 2 steps. So I know that V is equal to 2 pi R over T. So I get V is proportional to 1 over T. And then A is equal to V squared over R. So I get A is proportional to V squared. So basically what I'm doing to get how A and T are related, I'm plugging in 1 over T squared. I'm replacing the 1 over the period for my V. So I get A is proportional to 1 over T squared. So if you type this into your calculator, it's what we call an inverse squared relationship. It still looks like an inverse, just a little steeper. Okay. So what are some other things that we could take away from this? Doubling the velocity quadruples the acceleration. And doubling the radius, so that looks like A is equal to V squared over R. So if I put a 2 in front of V, and V is squared, my acceleration goes up by a factor of 4. And then likewise, A is equal to V squared over R. If I double the radius, I'm introducing a factor of 2 in the denominator, so I must do the same thing on the left-hand side of the equation, so it halves the acceleration. All right, so why don't you try out the next example. I will give you the answers in class. Okay? So thanks for listening. There's a second video that deals with the derivation on the next page, and there'll be a third video that talks about the last page of your note sheet. All right, so thanks for listening. Have a great night, and we will see you in class. Bye.